In this lecture, we're going to take a look at a couple of examples how we can use nonlinear regression modeling to describe patterns in data. And in this first example, we're going to look at something called the NFL Draft, which is an event that takes place every year that selects university players into the National Football League. And these data were obtained from the 2015 National Football League draft, which took place between April 30th and May 2nd. And this event has 32 teams in the league that selects players in a round by round fashion. So each team gets to select a player in each round. And in 2015, a total of 256 players were selected for the next group coming into the league for the next season. Now, the players that are selected in the first round are deemed to be the players of the highest perceived value in terms of their talent that they can bring to the team. And as a result, the salary paid out to the players selected early will tend to be higher than those players that are selected in the later rounds. One unique aspect of this draft is, aside from the salary paid to the players, is that players receive what's called a signing bonus. And the signing bonus is not a salary, it's a one-time payment that is made from the team to the player when that player signs a contract after the selection. And in 2015, for all the players, for the 32 players selected only in the first round, the average signing bonus was just over $7.5 million. But not all players in the first round receive the same value of the signing bonus. And that is quantified here in the standard deviation around the average for that signing bonus. And we see that the standard deviation is quite large here, indicating a wide degree of variability in how much money was paid out to each of the 32 players in the first round. Now, when we take a look at the median signing bonus in the first round, the median or the middle was an even $6 million. So what we can see here is that the median and the mean are quite a bit different from each other. And because the mean is higher than the median, that would tell us that the distribution of these signing bonuses was positively skewed, so that a small number of players that were paid very high signing bonuses skewed the average into that direction, into the positive direction, away from the median. Now, in this graph, what we're looking at is a descriptive graph of each of those signing bonuses for the 32 players taken in the first round. So if we take a look at the x-axis here, here we see this is plotted from the first selection all the way out to the 32nd selection. And we can see that the actual number paid out in the signing bonus, this is the actual value for each player, decreases as a function of the selection. So the very first player that was selected in 2015 received a signing bonus of almost $17 million. Once again, that's a one-time payment. And if we take a look at the last player selected in the first round, the 32nd player, their signing bonus was closer to about $4 million. So a very big difference. And we use regression modeling, specifically nonlinear regression modeling, and that's what you see here in the in this red curve. Is instead of a line of best fit, we have a curve of best fit. So the curve here is the best approximation that describes the change in the signing bonus as a function of first round selection. If we take a look at the average signing bonus, and here I just visually put this line here to where the average signing bonus sits, we see that there were only 3 players that had signing bonuses that were around the average. And if we take a look at the number of players that had signing bonuses above the average, we have 1, 2, 3, 4, 5, 6, 7, 8 players above average for the signing bonus, but below average we had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21 players. The majority of players in the first round were paid less than the average. And so what we see here is that the average does not always provide an accurate indication of the signing bonus in the first round. It gives us a one-time number, giving us a sense of it, but nonlinear regression modeling can give us a better idea. And what we see here, instead of having a line of best fit, we have a curve of best fit, and the equation is certainly more complex than a line of best fit, but the idea is the same. And the curve fits with an R squared value of almost 98%. So this is a very close fit of this nonlinear regression model. The second example relates to the COVID-19 pandemic. And recall that COVID-19 is a respiratory disease caused by a virus. That virus is the SARS-CoV-2 or coronavirus 2 virus. And this is a computer model of the virus that was known to infect many people. And the virus, acting as a virus, contains genetic information or genetic material that damages cells of humans. And that's what caused illness, disease, and death. And we see that this particular virus, as all viruses, have what's called an antigen. And that's a portion of the protein that caused the infection. Now, if we take a look at the data related to COVID-19, these are statistics for the week ending September 19, 2021, and these were obtained from the Johns Hopkins Coronavirus Resource Center online. And the worldwide case count at this effective of this date for this week ending, we saw that the worldwide case count was almost 231 million, with a death count of over 4.7 million. Specifically in Canada at that time, the Canada-wide case count as reported was over 1.6 million, with a 1.7% fatality rate, or the number of deaths divided by the number of cases. If we look at another date for the week ending February 28th, we see a much larger number of case counts worldwide, with a much larger number of worldwide death counts. And we see that the similar pattern followed in Canada, with 4.6 million reported in cases, with over 51,000 deaths, with a 1.1% fatality rate. Now, how can we use nonlinear regression modeling to get a description or an idea of these case counts? And so what this graph illustrates here are the number of new COVID-2 infections in Canada between July 18th and September 6th. And the triangles here, or rather the blue diamonds, indicate the new cases starting on July 18th at time 0 on the x-axis. And we can see that over this 7-week period, the number of new cases increases, but does not increase in a linear manner. There's a slow increase followed by a more steady increase over that 7-week period. And so if we take a look at week 7, for example, the week ending September 6, 2021, there were 25,342 new cases. And what this equation here is, this is the curve of best fit, exact same idea as the line of best fit with linear regression. And as you can see here, the fit of the curve to the data was nearly perfect at over 99%, not 100%, but over 99%. And so the curve provided a very good description to to follow that increase. And this is our nonlinear regression model. Now, what we see here on this graph is what's called a forecast model. And so the forecast model takes the previously generated model that was produced from the data and stretches the model and tries to predict the number of cases out to October 3rd. And so the question with nonlinear regression modeling when it comes to producing a short-term forecast is how accurate is this model? So you see an R-squared value of 1. This is based upon the fact that the triangles were generated from the model and not the observed data. That's why we have an R-squared of 1. And so by using this particular model, what this model produces is what's called an inflection point, which occurred on August 22nd. And so prior to August 22nd, we see an increasing rate of new cases, but those new cases, although they continue to increase, will eventually plateau and start to decrease. That's what a forecast model attempts to predict. So if we take a look at the quality of this nonlinear model, we see that the projected number of cases for the week ending September 12th, for example, which is 1 week after the observation on the previous slide, the actual number of cases for the week ending September 12th was 27,716. That's what was reported by Johns Hopkins. But the projected number was 28,773. So in terms of the value of the nonlinear model 1 week later, had an error of 5%. And so the nonlinear model was actually quite good in terms of predicting the number of new cases and by an error of 5%. So this ends this video on some examples of how nonlinear regression modeling can be used.